Good day once again, everyone, and it's such a wonderful thing just to meet you again. And as we continue to learn physics, and I'm sure you are working very hard trying to prepare for those exams. And if you're an educator, I'm sure you are also trying to equip yourself as much as you possibly can. Thank you once again for joining me on my channel. And by the way, we've reached a subscribership of 5,000. Oh, I'm so excited. And I hope we're just going to keep on growing and going further and further as I try to produce as much of quality content as possible. Now, today I want us to go through electrodynamics. It is not such a big section. However, it does have some nitty-gritties that we need to make sure that we understand. And hopefully, I'm able to deliver it quite well. And by the way, for those of you who have not subscribed, please do the right thing. Okay, become part of the family. Okay, and obviously, you are more than welcome to recommend the channel to as many people as possible. Now, ladies and gents, I want us to get right into it. Okay, let's go. Right, so first of all, electrodynamics is essentially a kind of a compound word. So it's made out of two words, which is the electro part and the dynamic part. So electro, this has to do with electricity, and this one has to do with movement. Okay, so in a sense, we are dealing with a relationship between movement and electricity. Okay, so as a result, under electrodynamics, we've got two devices that we're going to have. Okay, and the first device that we are going to talk about is a generator. Okay, so we've got a generator as well as a motor. So I'm just going to so we've got a generator and a motor. Okay, so those two devices actually are electrodynamic devices, but their energy conversions are different. Now, in a generator, the kind of energy change that takes place is, well, here we are basically converting mechanical energy, which means that movement. Okay, we are converting mechanical energy, all right, into electrical energy. All right, so as you know now, because HCOM has been doing a number on us, okay, so a lot of people are converting to using generators because they need that electrical energy, right? So in this case, we also have motor. If you think of a motor car, right, a motor car has a battery in it, and for you to get it started, that battery has to have power. So what you are doing here is you are converting, okay, look, I made a mistake here. So it's mechanical energy into electrical energy. Okay, sorry about that. In fact, I shouldn't have even erased that. So we are converting that into electrical energy. So that's from mechanical energy into electrical energy, right? And then on a motor, what we have is we are converting the electrical energy, okay, and we are converting that into mechanical energy. So if you think about it, they kind of operate, differently. The one converts mechanical to electrical, the other one converts electrical to mechanical energy. So if you think of a motor car, you've got that battery, you start it up, and then what does it do? It fires up an engine, and obviously you can move from that, right? So it converts electrical energy from a battery, and it converts that into mechanical energy, which is movement. Okay, right. So now what I just quickly want us to do is to talk about how these operate. Okay, so on what principle of physics, does a generator operate? Well, essentially, a generator uses what we call the law of electromagnetic induction, or simply put, we know that it actually uses Faraday's law. Okay, now for those of you in grade 12, remember that you are not necessarily, you don't have to know how to, define or give us be able to state Faraday's law. All right. All you just need to remember is that this uses Faraday's law. Okay. And obviously, in this case, we know that's the principle of physics that is used by a generator. And essentially, this one uses what we call Lenz's law. Okay, Lenz's law. So that's the principle of physics that a motor actually employs. Okay, that it uses. And so, ladies and gents, I want us to get into the nitty-gritties on it. Of course, I don't want us to spend unnecessary time trying to, get to that. But I know a lot of learners, struggle with that left hand, right hand, and all of that. Now, all I just want you to remember is that a generator, okay, will use Fleming's right hand rule. Okay, so I'm just going to say RHR, so that's a right hand rule. Okay, whereas a motor will actually use the left hand motor rule. Okay, so just remember, as I'm about to teach you this right now, just remember that we're going to use the right hand when it comes to a generator, and we use the left hand when it comes to a motor. Now, ladies and gents, one of the things that I'm not good at is drawing, okay? Because what I want us to do in the next few moments is just to show you how to use that right hand and left hand stuff, okay? So for me to do that, I would have to draw a very complex drawing, and I know I could have, just taken a structure from any other, textbook and so on. But I don't want to violate people's intellectual property. So what I'm going to do is I'm just going to draw a simple generator. Okay, just please keep in mind, whatever I'm going to teach you about a generator, remember we're using right hand rule. The same can be said for a motor, but I'm going to show you that a little later on. Okay, so I'm just going to draw a simplified drawing or diagram here, okay, of a generator. So you've got this guy that is able to actually turn. Okay, we usually call this an armature. So you have a wire that goes across like this. Okay, so this is the armature. This is the part that is able to rotate, and these are the axes of rotation. Okay, so I'm just going to use my calculator to just illustrate that to you. So if you think about it, if let's say this is your armature, all right, and it's able to rotate, so it should be able to rotate either like this in that direction, or it's able to rotate in that direction. Okay, so just imagine that panel there, or that armature there, being able to rotate either clockwise or anti-clockwise. Okay, just stay with me just a little while. All right, so in this case, we put a magnet. Now, ladies and gents, this is only for the purposes of illustrating what I want to show you just now. Okay, so you put a magnet, or we have magnets. Remember, it's the principle of electromagnetic induction. So we know we've got magnets. Now, just for illustrative purposes, I'm just going to have my magnet having a north pole this side and a south pole this side. Right, I want you to please stay with me so that I'm able to show you how exactly does this work. Okay, so let's say this is side AB, this side is C to D. Okay, right, now ladies and gents, let's assume this is a generator. I want to show you how to use the right hand rule. Okay, now what I want us to do is I'm going to give you two things, and we are supposed to predict the other. You'll understand in just a few moments. Just stay with me, as I said, right? So what I'm going to do is, let's assume this armature is rotating. and it's rotating clockwise. Can you see that? Okay, so if you're looking at this, okay, I'm taking my calculator again. So if you're looking at this, so this is our armature part, and it's rotating clockwise like that. Okay, so it's rotating clockwise like that. Now I want you to just imagine, okay, if it's lying flat like this. Okay, so I know that this side, so I want us to focus only on side AB for now. Okay, so when I'm rotating clockwise, where is side AB moving? Side AB is moving upwards. Now, ladies and gents, what normally happens is that when people look at this law or this principle on how it works, they kind of get confused. Okay, so how do I move my finger and so on and so forth, right? So I want you to always, now remember, AB on this diagram is on the left hand side. Okay, so even when I flip my armature, just remember that side AB is always the side that is on your left. Okay, right. So now we are rotating this clockwise. Okay, look at this. Where's side AB going? It's going up. It's coming towards you, right? Okay, so in this case, side AB is going up. Now, when I rotate this, remember this is no longer the left-hand side. This is your left-hand side now. What's the left-hand side doing? It's going up. So consistently, the left-hand side is consistently going up. See? Then it flips again. Where's your left-hand side going? The left-hand side is going up. So imagine this is your armature, right? And in your armature, it's rotating clockwise, and the left-hand side consistently is going upwards. Now, then we say, now please, I want you to note, don't worry, we're just going to go through it in just a moment. But what we also know is that magnetic field always moves from the north pole to the south pole of the magnet. So where's our magnetic field going? It's in that direction. Okay, right. So obviously, if I were to place north this side and south that side, okay, it means that it would actually turn the other direction. Okay, so in this case, there is my magnetic field. So my magnetic field will always move from north to south. Okay, right. Now, we said, first of all, the thumb will always show me the direction of rotation. Okay, sorry that my camera is going out of focus there because I keep disturbing it. Okay, so in this case, the thumb is always showing me direction of rotation. Now, please, I wanted you to note, on the left hand side, where is the direction of rotation? You said to me it's coming towards you, right? So my thumb is pointed upwards. So what we normally do is we place our fingers, okay, the thumb, the first finger, the second finger at right hand to each other, right? Now the thumb shows us direction of rotation, or you can say the thumb shows us the direction of the force, right? So when this guy is rotating, going upwards, where's the force going? It's going up, right? So it means that my direction of rotation is upwards. I hope that you can get that. It's rotating upwards. So on the left hand side, my force is going up. Okay, now we say that the first finger, okay, right, I want you to imagine, okay, so this is our forefinger or the first finger. We say that this shows us the field, first field, right? So in this case, our first finger tells us the direction of the magnetic field, right? So where's our magnetic field going? In that direction, right? Okay, so we're saying, all right, so the direction of rotation is upwards. Okay, our first finger is going up. Okay, so sorry, it's going from left to right. So there it is there. So where's the direction of my current? So it means on side AB, I'm trying to determine where will the direction of the current move on side AB. And in this case, it's telling me it's moving from A to B. Okay, so if you think about it for a generator, so I put it like that. We said I'm looking on the left hand side. First of all, it means that direction of rotation is going up like that. It's coming towards you, right? First finger, this is going in that direction. That's the direction of the current. And now this this is the direction of the field rather. And my second finger, second current, okay? So the direction of my second finger in this case shows me the direction of the current. So if you think about it, there it is there, right? Direction of rotation is upwards, okay? First finger is going in the direction of the field, right? And therefore my second finger is showing me the direction of the current. So normally they would have asked you in this question, show us where the direction of the current would be, all right, on side AB. So that's what you would do. Now let's just do this. Let's make sure that we can understand this. Let's do the same for the side CD and see whether that would be consistent, right? So if you think about this again as your armature, right, we are going to rotate it. Okay, can you see it's rotating clockwise? So if I'm rotating it clockwise, the side CD, where is it going? You're right, it's going down the page, right? So it's going in that direction, okay? So the side CD is going in that direction, it's going down. And where's the field going? Remember, field, we said it's north to south, okay? And as a result, where would be the direction of the current? Now I'm going to do it now, okay? So again, we said, all right, so this is going down the page. There is my field. And I'm not sure if you can see it quite nicely, okay? So the thumb is facing downwards. My field, there it is going in that direction, and there is the direction of my current. So direction of rotation downwards, so there it is there, it's going down, and we said field is still going north to south, and therefore the direction of my current would be going down, which is consistent, right? Because current would be moving all in that direction. I hope that makes sense, ladies and gents. Right, so this is when you are given a generator. Obviously, what would happen if you were given a motor? Okay, so I want to quickly do that for you, all right, and show you how we are going to do that for an electrical motor. Okay, right, so I'm just going to draw the same drawing, but how will you know when you have a motor? Okay, let's just take another page quickly. So how will you know when you've got a motor? So in that case, what you would probably be given, okay, as I did say, my drawing skills just need a lot of prayers, okay. Again, let me try and put my magnets. Okay, you know what? Let's do this. Let's do this. So that you don't think that magnets always are placed north this side and south. Let's put south this side, and let's put north on this side. Okay. Now, with a motor, what you probably will have, okay, is that we are going to tell you. Remember, a motor is connected to a battery. Let's say on this is the positive side and this is the negative side, okay? So if I connect it to a battery, right? So say this is the positive side and that is the negative side. So already what have I given you? I've given you the direction of the current. Remember, conventional current always says we move from the positive side to the negative side. So let's see. So it means in this case, I've given you direction of the current. Okay, there's my direction of the current. And so it means that even on this side, my current would be moving in that direction. So from positive, it's going to the negative side. I hope that you get that. So the question would be here. In which direction will my armature rotate? Will it rotate clockwise or will it rotate anti-clockwise? Can you see? So normally, ladies and gents, when they give you these diagrams, you'll always be given two things, and in a way they will ask you the third one. I don't want to waste a lot of time on this. Okay, because usually it's not really worth a lot of marks, even on the exam. However, I do want you to understand how it works. Okay, so we are given a motor this time. So now we want to know in which direction will it rotate. Which hand are we going to use? Please remember, we said with the motor, we use the left hand. Okay, so we're going to use our left hand. So now let's focus. Okay, let's say this is side PQ and this is RS. Okay, now to know where this thing is rotating, let's focus again on one side. Okay, so let's focus on side PQ. All right, side PQ, where is my current going? Okay, on side PQ, so this is my left hand. Okay, this will be a little bit challenging to do, but we'll try to do that together. So I'm taking my left hand. Okay, we're saying, all right, my current, remember, so we said the second finger shows us the current, right? So my current is going down, but my field, where is it going? North to south. Okay, so that's why I wanted you not to think that your field will always, or your north will always be on the left. So in this case, where's my field going? In that direction. Okay, so there's the direction of my magnetic field, right? So as a result, okay, let's try and do that together. Okay, so there is the direction of my field. That's my second finger. Okay, so I'm just going to move a little bit so that I can illustrate it better. Okay, so there is the direction of my field. Okay, so there's my left hand. All right, my field is in that direction. Okay, there it is. My current is going down. So okay, it's not within a perfect shot of my camera. So if I move it and position it like that, there's my current going down. That's my second finger. There's my field going in that direction. Can you see where my thumb is pointing? It's pointing downwards. Okay, so on this side, it means that the direction of the force would kind of be downwards. Okay, so what does that mean? It means that if this is my armature, if it's being pushed downwards on this side, so where would it rotate? So if it's pushed downwards on this side, so can you see it's going to rotate anti-clockwise? Okay, even if you decide to check side RS. Okay, let's try it with side RS. Where's my current going? My current is going upwards. All right, so there's my left hand yet again. So my current, remember it's the second finger. There it's going upwards. All right, my field is going in that direction. So I want you to think about it. So there's my left hand. So current in that direction. Current, there it is, going up on this side. Okay, going up. Field on the left hand side, and therefore where's the direction of the force? Can you see? My force will be upwards. So in this case, it means the force is going down on this side, it's going up on this side. So in this case, you'll end up having an armature that is able to rotate clockwise, anti-clockwise like that. Okay, so ladies and gents, just please remember, what we'll do is I'll post another video where I'm doing past exam questions, okay, in this section. What I just wanted you to grasp today is just the theoretical part of it. Now, let's move on very quickly to talking about AC and DC, whether generator or motor. Now, of course, we've got what we call a direct current motor, DC, okay, or a direct current generator for that matter, right? So you've got AC and DC, right? Now, what is the difference between the two? Of course, that current actually maintains the same direction for DC as well as AC. In fact, you know what? Let's try and put it in a different page. So you've got current that is going to move in a DC generator. Okay, I know that current would move in the same direction. Okay, So ladies and gents, we've got a graph that shows us the instantaneous voltage or current with time. Okay, so this would be voltage against time. This is for DC. Now, how would that graph look like? Okay, it would be a graph that looks more or less like this. Okay, where this would be the maximum. By the way, I didn't explain that part. So this would be the maximum voltage over there. All right, and then obviously the minimum would be 0. So DC maintains the same direction. So the reason why it actually keeps fluctuating like that is because, remember, as your armature keeps rotating, in this case, the amount of current that is generated, okay, if you think about it, so when it's standing like that, okay, you'd find that the current becomes 0. It doesn't generate any current. But now when it goes, if my magnets are sitting both on this side, so it would actually, you'd now have a maximum voltage in a sense. So for direct current would get a graph that looks like that. As I said, ladies and gents, you know, the thing about it is just to try and focus on the stuff that you need at this level. Okay, there's quite a lot of information that I can provide, but if it's not going to be to assist you, maybe rather let's not even touch on it. Okay, right. And then what about AC? So alternating current. The difference, however, is that now the current alternates. It changes direction. So what you end up having is a sinusoidal function like that. Okay, so this would be voltage with time. Okay, and that's time, or yeah, that's time in whatever, in seconds or milliseconds, whatever that is, right? So in this case, what may happen, by the way, with voltage, I can actually give you the average voltage with time. And what you simply do to calculate the average voltage, okay, so to get that average there, we say, well, that's going to just simply be V max. Okay, you take the mean of your maximum plus the minimum. Your minimum is 0. So V max plus 0 would be V max divided by 2. That would give us our average voltage. So you end up with a graph like that. So this would be our average voltage. Right, not that you need that quite a lot, but I want to explain something about alternating current. Now, oh, by the way, before I get ahead of myself, now, in the structure, okay, let's take again the structure of our voltage, of our just our basic motor or generator. How will I know whether I have a DC motor or an AC motor? Now, ladies and gents, I want you to please note that for DC we will use, so you'll see there, you'll see with the diagrams that I'm going to give you in just a few, right? So we have what we call split rings. Now split rings, they look something like that. Okay, so you've got split rings that we're going to connect to our brushes, right? So split rings, you remember that's DC. Now, ladies and gents, I always try to find ways in which I'm going to remember. I hate it when I go to the exam and I can't remember something. So what I said for myself, how will I remember that it's DC? All you simply do is say, well, this is C. This looks like a C and a D, isn't it? So when I see C and a D, then it means that's DC. Okay. Whereas if I use alternating current, right, we use what we call slip rings. Okay. So in this case, it will be full rings like that are connected right there at the end of your armature, right? So it will be full rings that are connected to your brushes. And by the way, what's the function of a brush? It's to make sure that there is electrical transmission through your armature and whatever device that it's connected to. Okay, so that is the function of your carbon brushes. Okay, so when you see your full rings like that are connected, so these we call slip rings. Okay, so these are slip rings, and these ones we call them split rings. Split rings. As I said to you, CD means it's DC, it's direct current. Okay, so they will normally ask you what type of a generator that is, and obviously you'll see from that structure. I hope you will be able to remember this. Okay, right, let's go back to our graphs so that we can get to the calculations quickly. Right, okay, so we said with alternating current. Now you remember with direct current, what we had was the average voltage gave us that. But with alternating current, look at that. If I take the maximum voltage, my Vmax there, okay, and my minimum, or in this case, this would be minus Vmax. Why? Because it keeps alternating, okay? It keeps changing direction. You'll notice if I take Vmax plus my minimum, okay, so it will be Vmax plus a minus Vmax, divide that by 2, you get 0. Okay, so imagine if we were built on voltage, right? We would not be able to get a reading. Okay, so we need to provide a solution for that. Okay, so I want you to keep in mind. So in this case, we're talking about an instance where we know that voltage would, or current rather, would follow the voltage, right? So if that would be a voltage with time, current with time would be exactly the same. Sorry about that. Okay, so current with time would kind of follow on the same trajectory. Okay, right. So in this case, we're simply saying this would be I max. Okay, right, and minus I max. Now, ladies and gents, what we simply are saying is that with alternating current, this is what we would experience. Okay, so now to try and solve this problem, because imagine if Eskom was going to try and find out how much voltage or current they're using. In this case, what you'd have a problem with is that it will always amount to 0. Why? Because it keeps going back and forth like that. Okay, so now how do they bill you? They don't bill you on voltage or current. They bill you on electrical energy, or in this case, I'm just going to talk about power. Okay, now what is power? If you remember from Ohm's law, we said power is voltage multiplied by current. Now you don't need to know all of this. Okay, you don't need to remember all of this. I'm leading you somewhere here, right? Now what happens? Then we say, okay, right, we know that voltage multiplied by current will always give us power. Now look at this. When my voltage is positive, my current is also positive. Can you see that? And I know a positive times a positive will give me a positive. So it means if this is a graph of power, okay, so this would be a graph of power against time, right? So in this case, positive times a positive would be a positive. But look at this, when my voltage becomes negative, my current also becomes negative. So what do I know? Negative times a negative will also be a positive, okay? So now the graph of power against time kind of follows what we had there. Can you see? Now, ladies and gents, we can say, okay, we can now find out what the average power is, okay? Now, if you remember, this would be P max over there, the maximum power, right? Okay, so how would I get the average power? I would say it's going to be P max plus 0, giving me, divide by 2 rather. So it would be P max divided by 2. Okay, right. Now, ladies and gents, for us now to calculate the average power, I want you to please note, it means to get Pmax, this would be Vmax, okay, multiplied by Imax divided by 2. Now, I wanted to find a way in which we can split this 2 into those into that product there, okay? And this is where we got Vmax multiplied by Imax, okay? Right? How do I split that 2? Well, mathematically, I can say square root 2 multiplied by square root 2. That would give me 2, isn't it? Now, I want you to please see this. Now we've got something very special here. Vmax divided by root 2, Imax divided by root 2, that gives me P average. Okay? Now we give these a special name. We say, well, what is Vmax divided by root 2? We call it the root mean square. The square root of the mean. Remember, when you say maximum plus minimum divided by 2, you are getting the mean, okay? I'm sure you've done stats, okay, in mathematics. So VRMS multiplied by IRMS, the root mean square. And what does that give us? It gives us the average power. Now, ladies and gents, I want you to note, whenever we calculate or whenever we are given power in this section, we are always going to be talking about average power. When they give me maximum power, remember, how do I get average power? It's going to be the maximum divided by 2. Now, don't even fret. Remember, you are given these formulas in your question paper. All right, I'm going to show you in just a few, right, that you are given all of those formulas. You don't need to stress about them. Okay, there, I'm going to take a past paper, a past exam question, right? All right, can you see that? Okay, so you are given P average, VRMS times IRMS. But what is VRMS? VRMS is Vmax divided by root 2. What is IRMS? It's Imax over root 2. And by the way, we also have other formulas. This comes from Ohm's law. If you remember, P is equals to V over R, V times I, P I squared R. Can you see? So to get the average power, we'll always take the RMS value, IRMS squared, multiplied by the resistance. Okay, and I'll show you applications on that as well. Okay, right, so I want you to please keep this in mind, ladies and gents. Okay, right, so I'm tempted to say, look, let's just jump right into a past exam question, and I'm gonna do more questions in the next video. Is that okay with everyone? All right, now I'm gonna take a question from a past paper here, and I want to do that with you. All right, so let's take the November 2020 paper. All right, and I'm going to do that with you. Okay, can you see that's November 2020? Okay, over there. Okay, from the Department of Basic Education, that's the NSC exam. All right, now they give us a simplified diagram there of an electrical machine that is shown. Now, I want you to please note. So first of all, what did they deliberately do? They connected this machine to a source, a battery there. All right. So what is it telling us already? They are converting electrical energy into mechanical energy. Can you see that? All right. And can you see those are your carbon brushes over there, those black things there? And they are connected to bracket-like thingies. Okay, so already I'm sure you can tell where I'm going with this. There's our CD. So what type is it? Okay, I'm sure you're getting what why I said what I said earlier on. So they say, is this machine a DC motor or a DC generator. Okay, so they've already told us it's a DC, right? It's DC, right? That's CD, that's DC. So is it a generator or a motor? It's definitely going to be a motor. Why? Because it's connected to a battery. So sometimes with a generator, what they would normally do is that connect this to a light bulb or whatever the case may be. All right, so there is no electrical source that is provided. Okay, right. And then they say to us the next question, write down the energy conversion that takes place while this machine is operating. Okay, so we've just said it is a motor, right? So it will convert electrical energy into mechanical energy. And then they say to us, write down the name of component A in the diagram. So it's our split rings, right? So those are the split rings. Okay. And then the next question, they say, in which direction will the coil shown in the diagram rotate? Okay, choose clockwise or anti-clockwise. So this is the part, ladies and gents, where I wanted us to apply what we had learned. You remember finger licking stuff, right? Okay, so in this case, we're going to say, all right, so we want to know in which direction will it rotate? Clockwise, so there's our armature there. And I did say to you, you only need to focus on one side, okay? So what I'm going to do here is let me label it. Let me call this side X, and let's say this is side Y, okay? Right, so I'm only going to focus on side XY. So if you think about it, here's my armature, all right? And I want to know whether it will rotate in that direction or whether it will rotate in that direction, okay? Right, so now what do I know first of all? I know that this is a motor. Which hand am I going to use? My left hand, okay? So I'm going to use my left hand. I'm going to say, all right, so the direction of my field north to south, so there it is there. It's rotating, it's going from north to south, okay? So there's my field, it's going north to south. And in this case, what else do I know? I know here's my current there. So positive side is this side. So it means that on side XY, current is moving from X to Y. Okay, so I want you to think about it. So look at this. There's my left hand. Current is moving left to Y. Remember the middle finger, this finger over here. All right, it's going from X to Y. So, all right, I'm trying to show it there. Okay, so there it is. My current is going in that direction. My field is going north to south. There's my current over there. And can you see where my force is going? Okay, so there's my force there. It's going down the page. So current is going in that direction. Okay, field in that direction. And therefore force is going in that direction downwards. So therefore, if the force is pushing this guy down on this side, on side XY, there it is, it means it has to be rotating in that direction, and therefore it is rotating anti-clockwise. Okay, so of course my choice there will be anti-clockwise. Now, ladies and gents, let's get to the calculations very quickly. All right, just to show you how straightforward the calculations are in this section. Right, so let's get into that part that you so wanted, which is the calculations on this guy. So they say to us an electrical device is marked 200 watts and 220 volts. Now, ladies and gents, I want you to please note, when they give us a device, so by the way, if you ever note on any device, electrical device, when they give us a power value, obviously power is measured in watts, right? That's 200 watts, and then just next to it, they give us, that's 220 volts. I want you to please note, the power that is given there is the average power, okay? And it means that the voltage that would be given there next to it would be the RMS value of the voltage. Okay, So what have they given us in this particular question? They've given us both the power as well as the average power, that is, as well as the average voltage, the RMS voltage for this circuit. And then they say to you define the term RMS voltage. Okay. I honestly don't like the definition part of this. Okay. Sometimes it may be a little bit daunting to just remember. Okay. But I want you to please remember that the root mean square, okay, is simply the equivalent of the steady voltage. So the direct current, it's the direct current equivalent, okay, of the other forms at the same average rate as the alternating current voltage. Okay, you can look this up in any book, and some give a better definition. I personally like the definition that simply says, okay, the RMS voltage is the alternating of an alternating current, right? Is the effective voltage for AC. All right. So it's the effective voltage for AC. So you can check other definitions, by the way. You can get other probably definitions that are a little bit better. But as I said, it's not very easy to get one that is very easy to remember. But nonetheless, let's go on to the questions. Okay, so they say to us, calculate the resistance of the device. Now, ladies and gents, I want you to please note. So what do they want? They want resistance. Now we've got three values, or three calculations, or three formulas for average power. The first one is VRMS times IRMS. Okay. The second one is P average is equals to IRMS squared multiplied by resistance. And the third one is P average is VRMS squared divided by R. Okay. Now you choose which formula you are going to use. But how do you choose a formula? You choose it based on what you have and what you want, isn't it? Okay. Now think about it. They gave us P average. All of those have P average. They gave us VRMS. So already it takes away this formula. Why? Because this one doesn't have VRMS. Can you see that? Okay. So this one has both P average and VRMS, P average and VRMS. But the question is, what do they want? They want me to determine the resistance. So obviously I'm going to go for this one, isn't it? Okay, so let's use that formula. So they said P average. We know that's 200. Now I'm substituting, right? P average. Please remember, we always write formula first as it appears on your book. Okay, so P average is VRMS squared divided by R. And then what do we now have? Now we're going to say what's our P average? That's 200. VRMS is 220. Now remember, if we had the maximum voltage, we'd need to first get VRMS by simply taking Vmax, that maximum voltage, and divide that by square root 2, right? So this time we were actually given the RMS value of the voltage. Now divided by R. So we are looking for R. Of course, what are we going to do here? We're going to cross multiply. So R multiplied by 200, that's 200R. That multiplied by 1, that's 220 squared. Okay, and obviously when we want R, this is simply going to be 220 squared divided by 200. Okay, so I'm just simply going to put that in my calculator. Okay, of course you'll do the same. Okay, so that's 220. Remember, we square that, divided by 200, and what I get there is 242. So it means that my device has a resistance value of 242. Now, all I just wanted you to remember is how do you pick out that formula. And please remember, you are given the formulas in your answer book. Right, so we are done with that one. They say now, okay, this device is now connected to a 150 volts AC source. So they tell us the very same device is now connected to another power source which has 150 volts. Okay, they want us to calculate the energy dissipated by the device in 10 minutes. Okay, now ladies and gents, what remains the same? Now note, when I change the voltage of the source, right, obviously it's going to change the amount of power that is actually dissipated. Okay, so now how am I going to get the amount of power, the amount of energy that is dissipated? Now I'm simply going to say, all right, now we need to find out. Remember, this voltage that's given, it's still our VRMS. Okay, so I'm going to say to myself, so there are two ways of doing this. I can either say, all right, from our formulas, let me just quickly show you there quickly how we calculate electrical energy. You remember from circuits or Ohm's law, all right? Now, it might not be given here, but I mean, you have it there, right? You know that when you want to calculate energy, right, this is the work done. So it's voltage multiplied by current multiplied by time, or you can just simply say use this one, which is the one that I'm going to use just now. Power is energy, work done, divided by time. It's the rate at which work is done. So let me use that one quickly. So meaning, let me calculate the power first. But what did I have for this question? Remember, I just calculated the resistance. It's still the same device, isn't it? Right? So it means that the resistance of this device remains the same, isn't it? So I know resistance. My resistance is 242. Okay, please remember that does not change. Okay, and then now I want to calculate the power. And what am I given, by the way? I'm given the RMS value of my voltage. They said it's 150 volts RMS, right? So now I've got R, I've got V RMS. I can definitely calculate P average. Which formula am I going to use between the three? I'm going to find the one that has VRMS as well as resistance. Of course, it's that one. So I'm going to say this is VRMS squared divided by R. But now my VRMS is 150 squared divided by R, which is 242. Please remember, that does not change. Okay, so I'm going to say 150 squared divided by, 150 squared, okay, divided by 242. Okay, I get 92.97. All right, so my 92.9, okay, let's say 98 watts. But now they didn't ask for power, they asked for energy. But how do I now calculate the energy that is dissipated? We know that power is the rate at which work is done. It's energy divided by time, isn't it? So I've got my power, my average power. I want to calculate the energy. And by the way, remember they gave me the time and they said it's 10 minutes. But remember, when they give me time, I need to use time in seconds, right? So let's substitute now. Average power, we said that's 92.98, which is equal to work done, which is what I want. And the time is 10 minutes. But how do I convert minutes into seconds? You're right, we multiply by 60. So it means when it comes to time here, yes, it's 10 minutes, but there are 60 minutes, there are 60 seconds in a minute. So I want to convert that into seconds. So that's 10 multiplied by 60 there. Okay, so I'm going to take that answer and multiply there 10 times 60. and I get a value for the work done. When we cross multiply there, we are going to get 55,785.12, and remember, energy is measured in joules. Okay, right, so that's one way of doing it. Okay, let me just show you the other. We could have used our energy equations. I could have just said energy is equals to V RMS. So it's from that energy equation. So it's V multiplied V squared multiplied by R, divide by R multiplied by time. Okay, so let me just quickly show you from the formula sheet so that you believe that it's true. So there it is there. So V squared multiplied by time divided by the resistance. So I could have just gone straight there and said, well, I've got my VRMS, that's 150 squared, multiplied by the time that I have, which is 60 seconds, but I've got 10 minutes that I'm given, right? So 1 minute is 60 seconds, so 10 minutes times 60, divide that by the resistance, which is 242. And believe you me, ladies and gents, it would have saved you from all of this. You'd still get more or less the same answer. Just going to round it off. Okay, maybe let me not do that. 785.12 joules. Okay, so that would be our final answer for the energy that is dissipated. Right, ladies and gents, I hope you can get the gist of what I'm trying to show here. Right, now I want you to please note I'm going to make another video wherein I tackle a different set of questions. All right, I didn't want to make this video too long, right? But if you benefited from this video, please don't forget to hit like, and please, ladies and gents, keep subscribing, okay? And tell even more people about this channel. If you are being helped, I'm sure you can spread the word around. Otherwise, I want to leave it here. Thank you so much. I hope that this section will not be a bother to you anymore. Thank you. Sharp, sharp.